Hello, I'm Lynn Langett. Welcome to part 4 of my 5-part series on understanding Hadoop MapReduce fundamentals. Now that we've explored looking at various types of MapReduce jobs, we're going to dive deeper into the subject of optimization. Now there's many different ways to optimize MapReduce, and of course it's critically important because we're dealing with huge volumes of data and we sometimes may have some resource constraints, particularly if we're being charged and we're running these MapReduce jobs in the cloud, for example. We also might have time constraints where we want to optimize so the results come back more quickly. I see this as a cycle as it relates to one or more MapReduce jobs. Now, in addition to the cycle of optimization of jobs, there is also optimizations that can be done to the physical environment, and by that I mean the Hadoop cluster. There are many configuration settings that you can adjust, and there is in fact, for the various distributions, multi-day administration classes that if that's your area of focus, I suggest that you do further study on. For the purposes of this course, we're going to focus on the MapReduce jobs and the chains of jobs. So before we go to the specific job, we can do optimization before the job runs, and we'll drill into that topic next. We can do optimization when we're loading the data. We can do optimization during the map phase of the job, which, to introduce the topic, often includes breaking complex mapping tasks into multiple jobs. We can do optimization of the shuffle phase of the job. We can do optimization of the reduce phase, and we can do post-processing or optimization after the job or job's complete. So the first thing is we might be reminded that the physical file size of an HDFS cluster is 64 or 128 meg blocks. So there will be certain situations where we want to adjust or pre-process the incoming files and filter out most commonly what doesn't have any value or junk data. In addition to that, we may choose to compress the incoming files. When the MapReduce job runs, the compressed files need to be uncompressed so that they can be processed, and sometimes there is additional compression applied throughout the lifetime of the MapReduce job. Although you may not think of this as an optimization, another potential optimization is encryption. And why I list this here is because there might be security or privacy considerations around the data, and if the data is encrypted or somehow obfuscated, this might affect the overhead of running a particular job. We've talked a little bit about pre-processing, and I've shown you some examples, and I've also mentioned this concept of writing your MapReduce jobs in a very functional way where they perform the smallest possible unit of work with a single type of process being performed rather than multiple processes. Now, to think more about compression, I took a page from the Cloudera book to use an example. You want to look at particular vendor distributions, and you also want to look at the version of the Hadoop binaries that you're working with to understand your compression options. So for this particular case from Cloudera's website, they talk about, and they've shown an example of uncompressed files and then files that are compressed with two different types of compression algorithms. They mention gzip, and then they mention LZO, which is notably splittable. So what that means is that when you are loading, if you have a splittable compression algorithm, that can optimize the load as well. So if you take a look here, you can see the size of the file after it's compressed, and you can see the time to compress and decompress. So these are very common considerations around the optimization of MapReduce, and often you'll do perf testing on small subsets if this is an ongoing batch type situation to figure out which type of compression algorithm is most appropriate and at which phases of the MapReduce job. Now, drilling into optimization possibilities within a particular MapReduce job, at the highest level you're going to look both at optimizing the mapper task and optimizing the reducer task. So some common optimization techniques around the mapper task are to define a custom input format. You also can work with custom input data types. You can define a custom partitioner. By default, MapReduce uses a hash partitioner, and there might be situations and types of data for which a custom partitioner might run more efficiently. I've mentioned several times this concept of splitting the process out onto other MapReduce jobs. And this is a very, very common optimization that I have worked with customers in prototyping in real-world situations. Another very common implementation is to add a local reducer. This literally is added in the job comp file, and it is an implementation of a reducer that optionally runs on each mapper as the mappers are running if there are records available. It's called spillage. Also, you can use map-only jobs. This is a very common implementation in chained MapReduce jobs or for particular types of business situations. For example, image processing. So you only need a certain type of transform to be applied to every piece of input. Now, optimizations around the reducer tasks, some of the more common ones are to split the process into multiple reducer tasks. And of course, you can configure reducer thresholds, so number of reducers based on the performance of the MapReduce job. So you can take a look here. We've got 2 physical nodes, and you'll be reminded that by default HDFS stores data 3 times, but that's configurable. And you can see we have these various points of optimization throughout the MapReduce processes. You can see the files are coming in via the input format. They are then split, and then we have record readers. The output from the mapper is, of course, key value pairs. And we have an intermediate output of key value pairs. Then the partitioner is implemented, which I just mentioned is by default a hash partitioner, which you can override. Then the shuffle and sort process runs. And then the reduce phase runs and outputs the final key value pairs in the output format and writes it normally back to the HDFS store. And of course, this runs across nodes. One of the other optimizations that you can do is you can set the level of replication. So by default, it's 3 nodes. You can set it to 2 or even 1 or up to 4, depending on what you want. You can set your output or your write back to other locations other than HDFS. We talked about using cloud-based locations or even the file system. In terms of subdividing tasks, sort of a baseline is to aim for 1 to 3 minutes per map task run. Mentioned implementation of a custom partitioner by overriding that method. I did talk about compression as an optimization technique. In addition to compressing the input files, you can also implement intermediate compression with the various formats so that there is less traffic going across the network when the intermediate key value pairs are sent to the reducers for ultimate aggregation. To better understand exactly what's occurring in your tasks, both map and reduce, you can enable various logging and counters through the MapReduce API. You can also allow the MapReduce API to skip over error data. And you can set up debugging and unit testing. So you have a lot of visibility into what is actually occurring during the MapReduce processes. One of the other types of optimization is monitoring or tuning for optimal spill ratio. The optimal ratio does depend on the type of map tasks being performed. The goal is the number of spilled records equals the number of map output records. And you can tune io.sort.spill%. Mentioned previously, but very common, is the implementation of a local reducer or a combiner. So this would be a reducer, a pre-aggregate on each mapper. Now, because this only runs if it is deemed necessary by the algorithm based on the use of memory, it's very important to understand that if you implement a local reducer, it's just a pre-aggregator and it should not produce output that changes the final output. It should just do intermediate level aggregation because it's not guaranteed to run. It depends on the amount of resources being consumed on the map. Taking a look at data types, you've seen through the various examples that we work with writables so that we can do processing through the MapReduce algorithm. So these are custom types that are part of the API. So we've got a text writable for string, we have an int writable, long writable, float writable, and boolean writable. If we're doing sorting, we need to use write comparable for keys. Now, if we want to implement a custom type then we're going to create that custom type in our MapReduce job, and we're going to write a raw comparator. You can perform what's called a secondary sort by writing that into your reducer task code. As you can with the mapper, you can implement logging and debugging so that you can better understand what the reducer is actually producing. And again, I'll mention you can subdivide tasks and chain jobs. A very common way to look to optimize MapReduce is simply to add more nodes. After all, that is a reason to use Hadoop, that it is scalable exponentially. So you certainly want to look first at that. And if that is not an option for you, then you have these various other options that we've talked about. On the slide, you can see debugging testing, logging profiling, subdividing, skipping bad records, writing more optimized Java, and something I hadn't yet mentioned is you can also implement what's called a distributed cache, which will bring lookup type data to each of the mappers most generally, so that they don't have to travel across the network to retrieve lookup type data. But again, if you're getting into that level of complexity, really take to heart here this ability to just add more nodes. To that end, I'm actually going to show you next a demo of me unit testing a MapReduce job. In this demonstration, I'm going to talk to you and show you how I unit test MapReduce. Now, there's a traditional approach using MRUnit, and this article from InfoQ has some really good information about the traditional approach, as along with using some other testing frameworks, Mockito, PowerMock, and I recommend that you take a look at it. In addition to using MRUnit, what I also use is I use an open source library called Approval Tests. So because I write my MapReduce jobs in Java primarily, the Java version of Approval Tests includes a specific set of extensions to test the objects in MapReduce 2.0. So let's take a look at how that works. My sample includes a download from GitHub with this approval test library. Switching over to the sample, I've got a sort of typical type of a job that does a variant of a word count, does something slightly different, which has a mapper, a reducer, and then rather than a typical test, it has the approval test in terms of files. And I'll make these files available as part of this course. This is on the Cloudera implementation. So you can see that I've got the mapper here, and it takes in a long writable text and outputs a text in an int writable. And it does some parsing of the input, the string parsing, and it looks at the words and pulls out the first letter basically and counts it. So in terms of the reducer, what the reducer does is it looks at the input, the text and the int writable, and it produces an output of text and double writable, and it takes an average of the particular values. Now, one of the great things about approval tests is because it gives you a visual output, and it's based on the golden master testing paradigm. When you first run it, the test will fail, and it will actually allow you to have a diff tool, so long as your IDE includes a diff tool, to bring up what is produced. In other words, what's the received is the name of the file, and then you can either say that is correct and rename that file to approved, or you can make the appropriate changes to your code and then make the next one the golden master. And then this produces a kind of a locking test, because once you have set what the golden master is, then subsequent tests against that will test the entire range of output, which makes it ideally suited to the output of algorithms like MapReduce, which generally outputs multiple values. So it's easier actually to show this in action rather than to explain it. So let me move over here to my sample code, and you can see I'm using approval test reporters, JUnit reporter and use reporter, and I've used my class attribute declaration to call the reporter, which will bring up the diff tool when this thing fails. And I have 3 different tests. Now I'm just putting in some string values for my data here. So I'm just saying hello world Llewellyn, and it's really, really fun, and Boston is cold. I originally wrote this when I was in Boston. Then I have a reducer, which has got a letter, which is expected as an output, and a count. And then I have the total job MapReduce, which tests all of it. Now if I want to run an individual part of this, I just click on the particular method and then I click run, and then that's going to fail. And basically here it's telling me what to do is that I need to go ahead and set this as my receive file as my golden master by renaming it to the approved file. But what I can do in the interim here is I can look at the output and I can see that the actual is for the map, hello world Llewellyn, it's really, really fun, and Boston is cold. And you can see what it's doing here. It's taking the first letter of each word and counting the number of letters in the word, so giving me a distribution. Now I can test this very, very easily without even bothering with the golden master by just simply changing the input string. So I can just say hello world Llewellyn, and now I can rerun my test. Of course it'll fail again, and now you can see I've got hello world Llewellyn. So it allows for an interactivity with a complex output that lends itself very, very well to testing MapReduce. The whole idea with approval tests is that it's a higher level set of testing rather than just a set of asserts around more complex objects. Again, this works similarly for the reducer. So in this particular case, I click on reduce and my input is H51. I go ahead and run that, and I bring this up, and you can see that this is showing an average here for the H. And again, if I play around with this value, and rerun the test, you can see that now my array value has changed, and I can check my math in this case, which is just an average, so it's pretty simple, but it allows me to unit test that input. Now, bringing it all together, I can bring in hello world Llewellyn, and I can test the entire algorithm. Again, I'm running this with a local distribution, so pseudo distributed with just one node, testing the logic of the particular MapReduce, not testing the performance in any way. And you can see the hello world Llewellyn maps the mapper here, maps the reducer here, and then that's my output. And of course, if I wanted to play with it, I could say, and it is sunny in California today. And then I could rerun this. I have to click on the actual method to just run that one method, which is what I want to do. And you can see that now my output has changed significantly. So I recommend that you use some type of testing framework in addition to the core MR unit. So you can take a look at the frameworks here on this InfoQ article, and or you can use the one that I use, which is approval tests extended for Java. I wanted to add a note about MapReduce 2.0. I mentioned early in the course, but I wanted to remind the listeners that there are two versions of the MapReduce API in current popular usage. In fact, many of the larger institutions, the financial institutions and the big healthcare companies that have been using Hadoop for many years in the social networks, still using quite a lot of MapReduce 1.0. So if you're watching this course and you're wanting to go out and do production work, you're probably going to want to also familiarize yourself with MapReduce 1.0 because a lot of the production code out there is in 1.0. Fortunately, the changes to the core API, although there are a couple of syntax changes, are not so significant that you won't be able to understand the code. I've actually written on both sides, and there are optimizations around high availability and scalability that are really important and you need to understand. But in terms of the core MapReduce API, 2.0 and 1.0 is quite similar. A quick way to tell what version that you're in is if you're working with for Java or .apache.hadoop.mapreduce, you're in 2.0. If it's MapRed, you're 1.0. The next area to take a look at is a highly complex library that can be used with Hadoop and HDFS, which will allow you to generate multiple MapReduce jobs and perform highly sophisticated calculations on the data input sets, and that's Mahout. So Mahout is a library with common machine learning algorithms. The algorithms are in the three general ML classifications of recommendation algorithms, classification, and clustering. So if you are not familiar with machine learning, this is not really for the faint of heart. I've been very curious about if somebody who did not have the opportunity to learn statistics in college could find use out of this library, because it really is very, very powerful. There is also a statistical analysis language called R. R is not designed specifically to work with Hadoop. There are some libraries you can install that facilitate that, but Mahout is the library that was specifically designed for this. There are, of course, third-party tools and some other ways to work with it as well, some GUI tools, but this is the sort of powerful thing, so I wanted to start with this. The algorithms include recommendation, which is likelihood. So an example of this is, Pandora Music or Amazon shopping baskets. Classification, which is you provide it with known data and then new data, and then it can identify what new data is most likely to be classified in the same type of group as the known data. So common business case is the identification of email spam. Clustering is when you have just groups of data and you do not have any sort of known value. So this is used, for example, to present stories in Google News. And if you are a statistician, this is a list of the currently supported Mahout algorithms. If you come from the Microsoft stack, that's the one I'm most familiar with. I'll call out a couple of them that were implemented on the database tools there, like the Bayesian algorithm, k-means clustering, fuzzy k-means, neural nets, different implementation, but there is a very small subset of these that you might be familiar with if you've worked with some RDBMS systems that have machine learning associated with them. Now for this demo, what I've done is I've set up the local version of the Hadoop binaries on Windows, actually set it up on Windows 8. And you can get this from the web platform installer, and this is for local development. I would think the most common scenario would be that you would have a local implementation and probably push it to the cloud to actually run production levels. So you get this from the web platform installer and you download the Hortonworks data platform for Windows. As I was talking about earlier, Hortonworks has worked with Microsoft to port the Hadoop binaries over to Windows, and then the Microsoft HD Insight Developer Preview. I would also recommend that you install the .NET Azure SDK, and because you're going to be working with Azure Blob Storage, and the Nudesic Azure Storage Viewer, which is a third-party tool that allows you to actually see into the contents of blobs. In this demonstration, I'll be using a local version of Hadoop on Windows 8, and I'll be running a Mahout clustering set of jobs, and you can then see what job chaining looks like with a very complex machine learning algorithm. In this demonstration, I'm going to take you through the steps for running a MapReduce job that uses the Apache Mahout library. Now for this one, I'm using Windows Azure HD Insight, and it has a lot of complexity to it, so it's a very interesting example in terms of getting closer to real-world MapReduce. So as said in the lecture, Mahout is a machine learning library. So the scenario here is we're going to use the million song data set that we've seen in some of the other examples, and we're going to set up and configure. We're going to examine and format the data, and we're going to do our processing using Visual Studio as a pre-MapReduce phase. So we'll be doing some data parsing through Visual Studio to generate some files, so I'll show you that step as well. Then we will be working with our HD Insight Azure instance, and we'll be installing the Mahout library, and then we will be running the job and examining the output. So I'm going to pause at various points so that this demo doesn't get too long. So the next step that I'm going to do is take you into the setup and configuration. In this first step of the demo, we learn a little bit more about the business problem that we're dealing with. So it's a Pandora-like recommendation output that we're looking for. So we have the million song set, and this just shows the format of the data, which is a common step in any sort of MapReduce processing. So as mentioned, one of the optimization steps can sometimes be to do pre-processing before running it through MapReduce. So I'll just briefly go over to Visual Studio and show you what this looks like. So it's nothing fancy, it's just a console app, and you have just pasted this code in. It's really all you did, nothing more than what you've seen before. Download the other file, and then in the properties, just set the argument and then put the directory where it should be, and then you go ahead and run it, which will then produce the output, and that saves the file to the output. So there you've done your pre-processing step, and I'll pause the video to get ready for the next step. Now in the next step, as it shows here in the instructions, you have to connect using your Windows Azure portal to HD Insight, to the management of it, and click on Remote Desktop. And so I'll just show you the steps to do that. So over here, and then you would connect to it by managing the cluster, and then you would just click Remote Desktop to Remote Desktop into it, which I've already done. And so once you remote desktop, then the next step is that you are going to install the Mahout version 0.7 zip file into the location where it needs to be. So I'll switch over to the RDP, and you can see that that needs to be under Apps and Distribution. So when I download it from this location here, so you can see here, it's a bunch of different jar files that you use, and it does include some other examples. So if you're really interested in the application of machine learning, there are other examples you can run here. So then the next step is to go ahead and copy the files that you generated on the local machine onto the remote desktop session. So that's pretty straightforward. You just go into your project location, and the two files that you created from the pre-process, you literally just copy them into the location that's needed for the particular sample. So just using copy and paste, you take these files that you generated in the pre-process, which are just your frequency, and then your users, which is actually a CSV. Then you take your users, and then the instructions tell you to create a single user, which I did here, and these will be inputs to the MapReduce job. So the next step is that you open up the command prompt for Hadoop, which is right here on the RDP desktop, and then using the command to copy, you copy the two files from local into HDFS, which is something we've seen in other demos. And then you can verify using the ls command that those files have been copied. So I'll just go ahead and do that, because I've already run this thing one time. And then you'll be able to see that. And I've set it for this job to run now from the command line using the similarity co-occurrence as the particular implementation algorithm. Now the job took quite a lot of time, and in the interest of time, I wanted to just show you job monitoring, because this is very important for understanding complexity and optimization. So I'm going to use the MapReduce status tool, and we'll just take a look at that. If I go up to my quick links, I can look at the retired jobs. So quite complex. So I started here with prepare preference matrix job item, and then I can click into that job, and then I can see that it was successful, that there was a map phase and a reduce phase, and I can look very, very granularly down to see how much information was read. And then I can look at the job XML, which is going to tell me even more granular information about the job itself. And then I can go back. I can see the status of the map and the reduce at the level of the job. Then I can go into the next part of this algorithm, which is a vector mapper reducer, and then I have a vector norm mapper. So for example, I can go into here, and again I can see information about the job itself. I can see that there were setup steps that were also successful. I can go in and I can see that. And here's the first attempt, and I can see even to the level of the machine. So then I can go back, and then just to bring this to completion, it tells me on the sample the Mahout job should run for several minutes. It actually took more than a half an hour, and then it creates an output file on HDFS, and here it shows you how to copy it, and then here's the output that you get. One of the questions I asked when I introduced this idea of machine learning on Hadoop scale data was, how can we get value out of it? Now, one of the big challenges is not only in selecting and applying the appropriate algorithm or set of algorithms, it is also in taking the output, which is, as I've shown here, just screens and screens full of numbers, and translating that into something that is usable by the subject matter experts. I've worked with various verticals: healthcare, biotech, financial, government, and there is a very big need for statistical analysis of these new big data sets, because just looking at them through the simple analysis methods really doesn't yield the richness of output that is possible. So is there any help for any of us to translate this into something that's more visually appealing and usable? Well, I'm going to circle back around to how I started this course. I do see many clients trying to use the tools that are available today, and the tool that's available for interactive query of data is most often Hive. Most of the people working with any kind of data have some experience with ANSI SQL, so even if Hadoop and any of the algorithms, including Mahout or machine learning, is new to them, they will try to use Hive. Microsoft has taken a very interesting approach to this problem by focusing on Excel. They have included with the HD Insight distribution a Hive ODBC driver that creates an interactive Hive query pane inside of Excel. In addition to that, using that same provider via ODBC, you can bring Hadoop data in and use Power Pivot, which is included with Excel 2013, to do mashups and presentation. Now, a new tool that's available is something called Data Explorer, which allows not only connection, mashup, and filtering, but it adds the concept of transformation exposed to the subject matter experts through Excel. So something that we would think of as using SSIS or maybe even some sort of Visual Studio task. Now, what's interesting about this is as the volumes of data grow and the complexity of job processes increases, it becomes very difficult to get meaning out of this massive amounts of data and to validate if the data is in fact correct. So I think it's quite an innovative strategy to push the data back down through to the subject matter experts, who frankly are going to understand the data probably better than any of the IT pros or the developers who are working with it. I've had great success working with various clients in various verticals, exposing them to these tools in Office. Now, there are other vendors that are doing interesting work in this area, and those include ClickView, working directly with several big data providers, Tableau, and Karmasphere. Karmasphere sits on top of AWS MapReduce and provides a GUI interface that allows for interactive visualization and direct manipulation of this type of data. Also, if you want to create your own client, there's a Hadoop SDK on Codeplex. In this next demo, I'm going to show you how executing Hive queries works in HD Insight. What you'll see is how the SQL-like language is very familiar. However, what you'll also see, executing a very simple Hive query will actually kick off one or more MapReduce jobs and will return significantly more slowly than we're used to in the relational world. In this next demo, I'm going to show you what it's like to pull through data from Windows Azure HD Insight into Excel using Data Explorer. In this demonstration, I'm going to show you how to run some Hive or HQL queries against HDFS Hadoop on Azure using the interactive console. So I'm going to start in the interactive console in my cluster that we saw earlier, and I'm going to switch to the Hive window. And inside of here you'll see I've got a couple sections, tables, columns, the response area, and then on the bottom where I can type in the queries. So for the purposes of time, I'm just going to copy and paste and describe the queries and execute them. So the first thing is I want to see any tables that have been defined on my HDFS cluster, and there's one in the sample. And you'll see that it's called Hive Sample Table. Now then I'm going to go ahead and take a look at the structure of this table by executing the describe Hive Sample Table command. And this will return the structure of the table, and you will remember that this is wide column. So it has names of columns and then simple data types. So these are the column names and these are the data types. Now I'm going to go ahead and copy in a query and explain it and then run it. So you'll see I'm selecting the device model, the market, the country. I'm running an aggregate, the sum of session ID against the sample table. I'm grouping by market, country, device model, ordering by country, and then returning the top 10 rows. Now, as mentioned in the lecture, this is going to kick off one or more MapReduce jobs as it executes. One thing to note is even though this is interactive, in that it'll return me a result that I can look at in the console here, it is not interactive in the sense that we're used to with SQL Server. So I'm going to go ahead and click Evaluate, and I'll note the time, which is 10 minutes after the hour. Now let's review the output. You can see that it returned correctly. And more important, we need to understand what it exactly did. First of all, it took more than 2 minutes. And if we scroll down, you can see it took this number of seconds. And it also launched 2 MapReduce jobs. So one of the reasons to use Hive is for quick exploration of data, relatively quick, of small subsets and sampling of data using a more familiar type of language. Do be aware that, of course, this is not interactive in the way that we are used to from the relational data store, and working against Hadoop size sets of data will result in very long wait times. Now let's just finish this off by reviewing what this looks like. You can see we have 17 jobs. If I look on the cluster, because I've run this a couple times, you can see I had some succeeds and fails. I can see if I go back in that if I click into here, I have jobs that were run for the description of the table, and then here's the actual information about this job if I wanted to look into it, and I could see the output, and I could see when the mappers and reducers were running and the amount of time that it took. So this is useful for many different situations, and most of the tools that come with Hadoop distributions include an interactive Hive console. In this demonstration, I'm going to show you accessing and manipulating HDFS data in some of the new Excel tools. So I'm working with Excel 2013, and I've installed a beta preview of something called Data Explorer. And this is similar to Power Pivot in that the concept is that you will mash up data, but it also includes the ability to perform lightweight transformations, ETL, or data manipulation from within Excel. So that's how it differentiates from Power Pivot. Also, you can save your mashups and you can send them for consumption to other services like Power Pivot or other data services. So this will allow you to connect to traditional sources like databases, files, so it's similar to Power Pivot in that way. But for the purposes of this demonstration, we're going to access HDFS data. Now you'll see from other sources here, I have the ability to work with HDFS, which could be local or a non-Microsoft distribution, but I'm going to work with HD Insight. So I'm going to go ahead and click on HD Insight. And then this is a little bit tricky. You need to enter the name of the Windows Azure Blob storage account associated with your HD Insight cluster. So I'm going to go ahead and switch over to grab that name. And to do this, I've selected my storage account and I'm going to click on Manage Access Keys. And I'm going to copy the name and switch back to the Data Explorer and paste it in. And I've previously copied my key in. So you can see there's a new type of a language here, and inside of here I can go ahead and access my HDFS data. And one of the ways I can know for sure is because this is in the format. So I've got success, part 0, part 1, which are the output of the various jobs. So if I wanted to go into here and work with this DaVinci information, I could click on it, and here is the actual information shown in a column. And then I would have the ability to create this into a table, for example, so do lightweight transforms. And this is a list of the various steps. And then I could do additional transforms. I could use the first row as headers. I could split. I could replace, so on and so forth. Now, if you're interested in the query language, it's a new type of query language here that is unique to this particular product, which is yet another way for us to work with various types of data. So you can see I'm actually accessing the data that's stored inside of the container. Now once I clicked OK on the query, you can see that this loaded inside of Excel, so it's just regular Excel data. And then I can bring back the query editor by clicking on Filter and Shape. That'll allow me to continue to mash up more data. I can enable download, load to the worksheet, or I can load to a data model. And the last thing I want to show you is once you've loaded your data model, you still have access to additional tools. So you can perform what's called quick analysis. And this can be quite handy when you've got Hadoop size data that you want to explore. So you can see here I've got text contains, duplicate values, there it's being highlighted, unique values, equal to, clear format. So very interesting tool. As of this recording, it's in preview. It's called Data Explorer, and I'll include the link to download it on the materials. So I've been showing you some different tools to help visualize the output of MapReduce jobs, starting with Hive and going into some of the integrated Excel tools. Now it's time to look at some futuristic stuff. I pulled this from one of the many visualizations that are available, and it really just shows what might be possible. So in this next demonstration, I'm going to show you a bit about a new language that was invented specifically for big data visualizations, D3, some examples of it, and show you specifically how a major organization is leveraging big data in a way through important, interactive, useful, and most importantly, differentiating data visualizations. And you're going to see all of this in my demonstration of D3. In this demonstration, I'm going to talk a little bit about some new data visualization options and show some examples from a new language called D3. So from Wikipedia, you can see that D3 is a JavaScript library that has been around for a couple of years now and is being widely used as a data visualization language. So you can read about D3 and where it came from and how to use it, including the technical principles. Basically, it's an embed with an HTML web page, just like any other JavaScript library on this Wikipedia page. In addition to that, I want to inspire you by taking a look at the D3.js site itself. And they have examples, but probably the most interesting thing here, in addition to the examples and documentation and source code, is these different basically visualizations that you can look at. So if you click on any one of these visualizations, and some have been more popularized than others, this type for example, you can see that I can basically play with the data. So this is a very, very important new aspect of visualization, this interactivity. and beauty in visualization. So they literally have hundreds of examples here to get you thinking, and I highly, highly encourage you to take a look at these. It's a little bit cut off because of my recording here. And I can click here and start thinking about whether, and here this is the gallery on GitHub where the source code is, whether it's you or somebody else on your development team, how you're going to visualize the output of your particular big data MapReduce projects. So you can see they have general categories of output going way beyond the pie charts and bar charts that we are most familiar with. Some of them are kind of familiar, more fancy stacked bars, if you will, and some of them have been around for a while, but maybe you've not used, such as a tree map, sometimes called a heat map. And some of them are completely new, at least to me, so I'd assume they'd be new to most people watching as well. Things like epicelical gears, which really gives us some new ideas about how we might want to play with the data, and some new possibilities in terms of visualization of more complex and larger amounts of data. So I encourage you to take some time when you're planning your particular projects to look at these various views. They really are just addictive. Here's the word cloud that we're all familiar with. So this is Twitter, Wikipedia, searching for the word cloud. Re-rendering. This aspect of creating data visualization, this is one of my favorite, animated Bezier curves. Now you can't tell me that's not fun. Is really an important aspect of the success of your project. Another couple here, rounded rectangle, that's a really great one. You can move it around. Now you might say, well, this is, fun and sort of neat to look at, but how does this have a practical usage? And here you can see there's really a lot of these. Another really kind of a fun one is directed graph editor. You can tell I like the graphs here. A lot of fun. Well, some of the people who are involved in the creation of D3 also have done some collaboration with large companies, and the one I'm most familiar with is the New York Times. And it's interesting as some newspapers make the transition into the big data age. Of course, a lot of them aren't making it. New York Times has actually hired a bunch of data scientists, not only to collect and analyze data, but importantly to help to visualize it in the online version of their paper, which has differentiated them and helped them to remain successful. So this is an example of an article with an interactive visualization in the science section of the New York Times from February 4th, 2012. It happens to be about testing among girls and boys that are 15-year-old in different countries of the world. So here it's showing you a graph and then has the associated article about the information, but really the sort of new aspect is to take this data and to create not only a graph that shows the result, which is girls outperform boys in more countries in a science test given to 15-year-olds, but in the United States, boys lead girls. Here's the interactive aspect of it. So you can see here they're showing countries in Asia and Northern Europe had high scores, and 15-year-old girls consistently outscored boys. You can see the grid over here talking about what color represents what, or the legend I should say. And then here you can see it's quite the opposite in the United States. And then going on, you can see Western Europe, it's a similar trend in Western Europe. Boys perform better than girls. And very different in Eastern, Southern Europe, and the Middle East. Girls did consistently better than boys. So again, this rich visualization helps to engage the reader with the data, with the text, and helps them to understand through a visual representation of data. So really important aspect of any big data project, and peripheral to understanding MapReduce, but important in that you want the output to be able to be useful for your particular end users. So this is D3, and going back to get started you go d3js.org.